Okay, everyone, I've pressed record. I hope you are having a good week 5. Remember, no classes for maths next week, week 6. It's very sad because I won't get to see you, but do enjoy it. In today's class, it's a calculus class, and the questions are from chapter 4 and chapter 5. In Monday's tutorial, I did quite a few questions from chapter 4. So I thought I would start with some chapter 5 questions. That way I'm not always doing the same questions because, you know, like there are a lot of questions to do. There's like 50 questions or something for this week, which is a lot. So I thought I could start with the mean value theorem and chapter 5. So let me know what's happening in the chat. This is a tutor-led tutorial, so I'll be helping you through the different questions and the different solutions to them. So I thought I would start with MVT. You down with MVT? Yeah, you know me, right? So the MVT really is just an average value theorem. So in this context, I don't mean that, you know, it's a really mean, horrible theorem. They mean the mean is the average. Okay, I'll draw a picture in a sec. The mean value theorem can be used for all sorts of things. In this question, we're asked to find a real number C that satisfies the conclusions of the MVT for, say, this function on this interval. Okay, so let me share something, a picture with you. Did somebody say GeoGebra? And we can have a look at what this mean value theorem looks like. So I'm going to put up GeoGebra for a second. Here we go. Okay, so here it is, and I'm going to put in the function root x, and I'm really only interested in that function on the interval from x equals 0 to x equals 2. Okay, now watch what I do. If I draw a line or a line segment from this point to the end of the interval, so I'm sort of drawing a straight line, what the MVT says is that there's some point where the slope of the curve is the same as the slope of this line. So let me put in a tangent line. Oh my goodness, can you see they're parallel lines? They are parallel lines. So there's some point, in this case it's at one, I think it's 1/2, right? Where the tangent line is parallel to the line joining the endpoints of the curve on the interval. That's it. That's all the mean value theorem says. Now, in this picture, there's only one point where that's true, but there could be more than one. Okay? So that's pretty much it. So let's have a look at the question in that we're looking at. So let me just get my notes. Okay, so I'll share my document camera with you now. So much sharing. Okay, so this is chapter 5, page 107. Question 1B. All right, so we're going to let a function be defined to be the square root function, and we're interested in the x values between 0 and 2. Okay, and the question asks us to find a C, a point C, such that the conclusion of the MVT hold? So what is the conclusion of the MVT? So let's remind ourselves. The conclusion of the MVT says the following. There is at least one point C, and it's strictly between 0 and 2, such that the slope of the tangent line is equal to that. Okay? So we want to find the C that satisfies this. Okay, so that's our function, that's our interval. Let's work it out. Okay, so we have the right-hand side of this expression is going to be root 2 minus root 0 all over 2 minus 0. Sweet. And so we simplify that to 1 on root 2. So now because we know our function, let's differentiate it and plug in x equals c. So if I differentiate this, I get 1 on 2 root x, and I'm evaluating it at x equals c. So let's make these two things equal, and we're going to solve this equation for c. All right. So we're going to solve and so let's just sort of, I guess we can change it around, right? We can bring the root c up there, the root 2 up there, and simplify. So c is going to be a half, like we expected from our picture. Okay. So that's a pretty easy question to do, because all you're doing is trying to find the c, because they're saying, well, use the conclusion of the MVT. All right. So that's probably an entry level kind of question for these kinds of problems. All right. The most important conditions for the MVT, you want the continuity and you want the differentiability of the function. Okay. All right. What else have we got here? Well, let's have a look at number 3. So keep the questions in the chat if you want to ask any questions about what I'm doing, or if something's not quite clear. All right. So question 3. Consider the function f given by this crazy function. Oh my goodness. Use the MVT to show that f dash has a 0 on this interval. Okay, so let's have a look. Did somebody say GeoGebra? Well, let's use GeoGebra. I'm going to do this without actually differentiating this function. And I think that's the way they want you to do it, right? Couple of questions in the chat. Habib, do you need a closed interval for the MVT? Yes, you do. You need the function to be continuous on a closed interval and then differentiable on the open interval associated with that. Taj, how do you choose an interval? Sometimes just trial and error. If you have GeoGebra or some other graphing software, that's usually very, very helpful. But sometimes you just need to try some things first. I don't know if there's any particular strategies associated with that. Okay. All right. So how do we do it? Well, like I said, did somebody say GeoGebra? Let's have a look. Oh yeah, there we go. So let me take this one off from the previous question. And you can see here, oh my goodness, look at that function. It's all right. Hopefully nobody's having like a seizure or something. We're working on the interval 1, x equals 1 to x equals 3 here. Yeah? Okay, so in the chat, yes or no, right? Does this graph have a zero derivative between x equals 1 and x equals 3? Okay, Zach says yes. CG, yes. Ziling, yes. Swetha, Andy, Taj, Jinqing, Habib, yes. Okay, and Zach, you're already reading my mind. It obviously happens at x equals 2. Okay, so just from the graph, we can see, yeah, hey, what they're saying or claiming is definitely true, and it definitely happens at x equals 2. Okay, but that's not the way they want you to do this question. It's great having GeoGebra, but they don't want that. But I would draw the graph anyway, right? So let's see how I think they want you to do it, and I'll just share my Chrome tab again. So here we've got, this is question 3. So our function is a crazy function. It is x minus 2 to the power 4 times cosine, and I've just factored this thing in the brackets. Okay. All right, and we are interested in that on this interval. Okay. All right. So what we want to show is there is at least one point. Yeah, it is. Yeah. Thanks, Zach. If you can't read it, by all means, let me see if I can get that a bit clearer. Hopefully that's a bit clearer. Okay. We want to show that this function has a derivative that's 0 between 1 and 3. Okay, so the question here is, does this function satisfy the conditions of the MVT? All right, so the MVT has two kinds of conditions here. Okay, so the first question you ask is this, and the second question is this. Okay, so is f continuous on this interval? Is f differentiable on this interval? Okay, now obviously from the graph that we put up before, both of those things are true. Okay, but let's say you didn't have a graph. Can anyone suggest why is the first part true for this function? Can anyone suggest how you might justify it, even if it's informal? Let me know in the chat. How might you, convince your friend or your teacher or whoever? Oh, Sam says elementary functions. Okay, I like that. So, so this is a polynomial. This is a trig function. This is a polynomial. You put them all together, you get something that's not only continuous but also differentiable. Is that what you're thinking, Sam? Yeah, Amelia, right. Yeah, yeah, we're on the same page. That's great. Thanks for that. So we can definitely tick these off. Yep, yep. So what that means is the conditions of MVT are satisfied. So let's do it. So by the MVT, there is at least one C between these points such that, so the ST stands for such that, okay. So what is f of 3? F of 3 is going to be 1 cos 1. What is f of 1? 1 cos 1. Da, 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 da. Yeah. So there you go. So there is at least one C such that the derivative is 0. Okay? QED. All right, a couple of questions in the chat. Zach, as long as its constituents are continuous and differentiable, the whole function is, yeah, as long as you're not dividing, Zach, and doing things like that, usually the answer is yes. Okay, so products, things like that. So just need to be careful when if you're dividing, for example, such that tau run, such that, yeah. Thank you, Lucas. Andy, do we need to write anything to prove f is continuous and differentiable? If I wanted to write something, I would just say f is the, it's the product of two functions or the composition of functions that are all continuous and differentiable, right? So if I wanted to write something more, note that f is composed of continuous and differentiable functions. And so f is also continuous and differentiable. Yeah. Okay. So this is not a difficult question, but like you say, a little bit of thought is needed here by actually showing that or justifying why the MVT conditions hold. Okay. Okay. So Zach, when we talk about differentiability, right? If I go, it's a really good question. So let me just go back to my picture here. Okay. So you should be able to see that, right? What does it mean if a function is differentiable? Yeah, like strictly speaking, the derivative is defined at all points in an interval. So the limits exist that make up the derivative definition, but it's easier just to look at it from a picture. This is what's known as a smooth curve, right? There's no spikes or corners or jumps, right? This is, I know just by looking at this curve that it's a nice smooth curve, okay? And that's another way of graphically looking at differentiability, okay? Amelia, because the question is why is it that we didn't have to differentiate? Okay, so that's a really good question. So let me just go back. Okay. First of all, this is not a nice function to differentiate, right? So we want to work smarter, not harder. Okay. So this is not a particularly nice function to differentiate. You could do it, but I wouldn't do it. Here, we're showing that the conditions of the MVT hold. We're not interested in the value of C. We don't care what C is. All we know is it's between 1 and 3. Okay? In the previous question, they asked us to do something different. They asked us to find the value of C. Okay? But here we don't care about it, right? Here we don't care. As long as it's between 1 and 3. Okay? So if I go back to the question, right? If I go back to the question, let me just share my PDF. So question 3, use the MVT to show that f dash, the derivative, has a 0 on this interval. That's it. We don't need to find the value of C to show that the derivative is 0 at some point. Okay? So that's quite a subtle, it's quite a subtle idea there. You don't need to find it, find something to show that it exists. Okay, that's one of the amazing things of the MVT. Okay. Ling, the question is, the function is differentiable for all points or only within the intervals? Well, it doesn't really matter, because what we're interested in is applying the MVT to a particular point. So all we're interested in is this interval. We don't care what happens everywhere else, right? We don't care what happens everywhere else. But this should be continuous and differentiable everywhere at all x points. Yeah? But strictly speaking, we don't really care, because this is the interval that we're focusing on. Okay. So, all right, Lucas has a question about Q2. All right. I think we can do that. Okay. So let me share my screen. We'll go back to the PDF. All right. Question 2. Suppose that this is our function, and show that it's impossible to have a C in this interval such that the derivative of this function at that point is equal to this. Okay, so how might we do it? Let me just have a look at my notes here. I think probably just drawing a picture would probably be enough, but let's see what we can do. So in this case, we want to show that it's impossible to have to get the conclusion of the MVT. Okay. All right. So let me go back to my document camera. Okay. So this is now question 2. So let f of x be 1 on x. And of course, x can't be 0 here. Okay. And the question is, show no C exists such that, ST is short for such that, I guess it's here, right? This is the way they've done it. Okay. So how do we do it? Well, let's work out the right-hand side. Okay. So RHS is right-hand side. So what is f of 2 minus f of negative 1? You get a half minus that all over 3. Yep. So what are we going to get? We're going to get 3 on 2 all over 3, which will be a half. Okay. And the left-hand side, so the derivative of this is going to be something like this. So we differentiate this function and then plug in x equals c. Okay. So now, this is, if we combine these, we're basically trying to solve. Now, is there a problem with this equation? What's the problem? What's the problem? Obviously here c can't equal 0 as well, right? Yeah. You're squaring something and you're changing the sign and you get positive 1/2. Yeah. So this is, we broke maths. Okay. So obviously this leads to a contradiction. So no C in this interval exists such that that's it. Ah, yes. When the mathematics all works out and we're smiling again. Okay. We broke maths. Okay. So that's one of the ways that you can solve this kind of problem. This function, it doesn't satisfy these conditions on -1 to +2. It doesn't satisfy those conditions. So you can't apply the MVT here, right? The conditions of the MVT do not hold. So you can't say anything involving the MVT with this function. Okay. Lucas, is that helpful, buddy? Cool. Cool. All right. So let me show what you can do with the MVT. So let me go back to my PDF. Okay. So I think question 5 is a good one. What I would like to do, I'll do parts A and B, and I'll leave C for you to do. Maybe you can have a go in the chat or something. But the MVT can help you with mathematical connections and inequalities. So the first part, which is the easiest part, use MVT to show sine t less than or equal to t for t positive. Okay. So that's pretty easy to do. Before we do that though, did somebody say GeoGebra? Let me show you what this looks like in GeoGebra. Okay, so let me just give me a second. And X. Yeah. Okay, so let me show you GeoGebra. So here it is, okay? The orange curve is the sine curve, and the purpley curve is just the line y equals x. And so, you know, if I zoom out, it's not true for negative values, but over here, it just keeps on going and going, and sine x just oscillates, okay? So we would think that it's true from our picture, but how do we actually prove it? And what does the MVT do here? Okay, so question 5. Let's show, this is part A. How do we even do this? Well, what we're going to do is define a new function, in this case, based on this left-hand side of the inequality. Okay, so I'm going to let a function be sine x, and I'm going to put that on this interval. Now, when I use this notation, students sometimes get nervous, right? They're like, "Ah, Professor, why is the t there and the t there? And well, what is the x for?" Well, don't be nervous. What we're doing here is we're going to get this, but to do it, we want to make the end point of our interval t, okay? And you'll see how that helps in a second. All right, so is sine x, who can tell me in the chat, is it continuous and differentiable everywhere? Who can tell me? Yeah, and it comes back to being a nice smooth curve, right? So let's make a note of that. It's continuous and differable everywhere. So what this means is you can apply the MVT to intervals like this. Okay, so by the MVT, yeah, you know me, there is at least one C. So now I'm working on this interval, okay, such that okay. So remember f, we've defined f to be the sine function. So what I'll do, this will become sine t. This is sine of 0, and this will become t minus 0. So I'll just write that around the other way. Okay, so I've written this part up here. Okay, what is the derivative of the sine function? Cosine. And I'm replacing x with c. Okay, now let's simplify. That's 0, that's 0. So we have this. Yeah, thank you, Andy. And what is an inequality for cosine function? What is cosine always less than or equal to? Who can tell me? What is cosine always less than or equal to? So what have we got? We've got sine t less than or equal to t. Oh my goodness. That is equivalent to star. Hooray! Yeah, how good is that, people? How good is that? Okay, where did cos come from? Zheng Yu, that's a good question. How you get cos? Cos is the derivative of sine. Yeah, thanks, Andy. Okay, so that's it. That's all you need to do. So students freak out when this is probably the most difficult notation. You want to have an interval where there's like a little variable, if you like, in the interval, and define a new function in terms of a different letter or variable. Okay. Fard, that's a good question. Okay. So did somebody say GeoGebra? Let's have a look at cosine. So it's a really good question. I'll put it up. So Fard, you should be able to see that's the cosine graph, yeah? That's the cosine graph. Now the cosine graph just goes between +1 and -1. So it's always less than or equal to +1. So that's where the inequality has come from. Yeah. If you see this graph never goes above 1. Okay. So that's where here to here comes from. Okay, I can say that this is true for all C. Okay, for all C. So I'm good with that. Does that help, Fad? Yeah, no worries, mate. That's all good. Okay, let's do one more question. Part B. Okay, this is a bit more subtle. Okay, this is a bit more subtle. So let me go back to my PDF. Okay, in part B, they want you to show that sine of t is not just less than or equal to t for t positive. They want sine t to be less than t, strictly less than t. Oh my goodness. Okay, so what we can do is use some of the arguments in part A. Okay, Zach, so if you remember the picture, C is the point where the slope of the tangent line is equal to the slope of the line connecting the endpoints of the graph. That's it, right? So yeah, that's it. All you got to do is draw a picture, and you'll get a good understanding of what C is. So let me go back to my document camera. Okay, what I can do here, if I wanted to show the sine t strictly less than t, so not less than or equal to, we change this to that. All we need to do is just think about our way of arguing here a bit more, and it's got to do with this. Okay, so I'm going to break it up into two parts. Okay, let me just check my working. All right. So part B, to show that this is actually true. We're actually going to use a little bit from part A. We note from A that sine t over t equals cosine c. Now, as long as c isn't too big, cosine is not just less than or equal to 1, it's strictly less than 1. Okay? So, for example, as long as t, and therefore c, are less than 2 pi, this thing has to be strictly less than 1. Okay? So that all you got to do is look at the graph of the cosine function to work that out. So what we can say then is, okay, well, that can go up there for all t. So we haven't quite finished the question though. So that's our first conclusion. But what about if t is greater than or equal to 2 pi? Well, that's super easy. Then we get the following, right? Let's think about this. Sine t on t, that's going to be less than or equal to, t is bigger than that. So we get that, right? I'm dividing, so I flip the sign. That's less than or equal to 1. And this is less than 1. Okay. So that's the second part of this. So you've got the inequality you want on this interval. You've got the inequality you want everywhere else. You combine them and you've done the question. Whoa! Wahoo! Okay, so pretty good, right? Pretty good. The way I've done it is to split it up into two parts. There may be other ways of doing this problem, but look, I think it's I think this is a very simple way because you're just using it on an interval and you get the other one for free. Okay, so yeah, I really like that solution, but you may have other ways of working or other ideas. That's no problem. Okay. All right. What else can we do? I think I'll leave C for you to do. Yeah, I think I'll leave C for you to do. Let's do a quick one because I've only got a few minutes left. I wanted to talk a little bit about error bounds. So let me pull up the PDF and there's actually a video there for that one. Hang on. Let me just see which one I'm going to do. So just bear with me for a second. Okay. Just having a look through my notes. Just keep learning, everyone. Just give me a second. Yeah, okay, this will do. I'll just put this up because this is something that I've put out earlier. I can zoom in as well, so just hang on a sec. Let me see if I can zoom in a bit. Hey, yeah. All right, so this question is very similar to question 7, okay? This is very similar to question 7. This is one I've done sort of just from my private stash of notes, okay? So you've got a function, you want to estimate some sort of difference, some error between something that's easy to calculate and something that's not so easy. And what you can do is start with this mean value theorem idea up here and apply the absolute value to both sides and then get some sort of inequality, okay? So this, to do part 7, it's very similar to the question that I've got here. People get a little bit frustrated with these questions because they talk about error approximation and stuff like this, but actually what you're doing is really starting with the mean value theorem and you're forming some sort of, you do the differentiation and you form some sort of inequality. This function's a decreasing function, so you can always, find some sort of upper bound for this thing here. So in this case, it's on the left. Okay. Now, Zach, I'm looking at your question. Would the approximation that sine t is approximately equal to t be a method? Approximately equal to t. Yeah, I guess, I mean, for small values of t, both t and sine t are small. Yeah, I think that's fine. I think that's fine. So this one's a little bit different to question 7. I think you've got, 16 and 17 or something like that. But the idea is exactly the same. The method is exactly the same. Work out the derivative, start with this, apply the absolute values, work out the maximum of this, and you can't quite see it, but here it is. That's like the derivative. And it's a max, because it's a decreasing function, it's a maximum at this point. So that's where this thing comes from. Okay. All right, folks, it is time to say goodbye. So look, like I said, I won't get to see you next week. I'm really sad. I think there's something in my eye. But just enjoy week 6. Good luck if you haven't done the lab test yet. Okay. I'll miss you next week. I hope you get a good break too. And watch out for that writing assignment. Thank you once again. Yeah, Zach, next week is there's no lectures or tutorials, but you can keep working and keep reading and writing and stuff. And yeah, the Yoshi folks are in the house. Always try to update the toys. And yeah, I'll see you in week 7. And feel free to reach out if you have questions or anything like that. All right. More music in week 7. Stay tuned. Bye, everyone.